Welcome everybody for our second day. We'll have 2 talks today and a very long lunch break. Yeah, very long. I mean, now, yeah, okay, very long. Our first speaker today is Julia Woolf from University of Cambridge. She'll be speaking on higher order generalizations of stability and arithmetic regularity. Okay, so thank you.
Well, thank you very much for the introduction, and also to the workshop organizers for the invitation. It's a great pleasure to have the opportunity to speak here. This talk will give some motivation for and an introduction to my recent joint work with Caroline Terry. So those of you who are at the Fields Institute at the moment will already have heard her speak on this. I will come at it from a different angle, but I will try and make sure that the talk is as self-contained as possible. 1 hour is not a long time to talk about 2 projects of this size, so I will be able to say very little about the proofs, unfortunately. I will also be very informal, so we will refer you to our paper in particular on the arithmetic regularity for a more abstract framework for phrasing some of these results, namely in terms of hereditary group properties that I'm about to present. Good. And the final caveat that I'll make is that everything in this talk will be about elementary P groups. I'll say a bit more about general groups at the very end of the talk. So to start with, I want to highlight a very common theme in arithmetic combinatorics. Combinatorics more generally, also number theory through the ages, namely the structure randomness dichotomy. The first thing that I think tends to be a little surprising to people is that randomness is in fact welcome. And this is because it enables us to count. I've put randomness in inverted commas because it is not just a randomness, true randomness that helps us count, but anything that makes our object look like a random object. And the second side of this dichotomy is that in the absence of such randomness, or even pseudo-randomness, we can find structure. And so this dichotomy underlies the proof of many results in arithmetic combinatorics in particular, such as, for example, the proof of Semradi's theorem on arithmetic progressions, but it is also has also been exploited in other fields such as ergodic theory. One way to make this dichotomy explicit is via a so-called regularity lemma. It's probably the single most powerful tool we have in combinatorics, and the story, at least the modern story, would naturally start in the 1970s with Semradi's regularity lemma for graphs. But I won't be talking about graphs today, so we'll jump straight into the group setting. So first of all, I need to explain what an appropriate notion of randomness or pseudo-randomness is in the setting of groups. And for that, at least for the duration of 1 slide, I will need the Fourier transform. So I will be looking at a function f from f2 to the n. That's an n-dimensional vector space over a field with characteristic 2. Let's say it's into -1, 1. And then for any r in f2 to the n, I define f hat of r, that should be, as the expectation over x in f2 to the n of f of x times -1 to the x transpose r. This expectation is simply the sum over all elements x in f2 to the n divided by the number of elements in that group. And I picked f2 to the n here for a particular reason, which you will see shortly. But of course, I can make a very similar definition for other prime characteristics. So this definition, is I'm sure you've seen something along these lines before. It has all the usual convenient properties, such as, it comes with an inversion formula and Parseval's identity, etc. But the important thing for us today is that if I set the function f equal to the characteristic function of a subset of f2 to the n, which I'll call a, then the magnitude of this Fourier coefficient f hat of r measures the following discrepancy. It measures the difference between the number of elements in my set that lie on the hyperplane x transpose r is equal to 0, and the number of elements in my set that lie on the hyperplane, the complementary hyperplane x transpose r is equal to 1. This means that if this Fourier coefficient is small in absolute value, then the set A is roughly evenly distributed across these two complementary hyperplanes. So in that sense, it has some of the properties that a random set might have, and we call a set A with the property that all of its non-trivial Fourier coefficients are small in absolute value, uniform. Now, I said this is a property that a random set has. There is another way in which a uniform set behaves, roughly speaking, like a random set. So I will present to you the following fact, which I will not prove, namely that if a set A is uniform, then it will contain approximately the number of three-term arithmetic progressions one would expect in a random set of the same density. So A looks like a random set when it comes to counting the number of three-term progressions in it, if it is uniform in this sense that all of its non-trivial Fourier coefficients are small. Now you might ask, all right then, so if the set A looks random in this sense, and I can count structures such as three-term arithmetic progressions, what if it is not random looking in this sense? Well, by definition, it will have a large Fourier coefficient, and we can use the information contained in that large Fourier coefficient to extract some structural information about the set A. I'm not going to explain to you exactly how that is done, because I want to jump straight to the the output of that process. For that, I need to make one more remark that, of course, I'm talking about the set A being uniform, and this would be, relative to the whole group F2 to the n. If I want to talk about A being uniform with respect to a subgroup of F2 to the n, then I can consider a relative Fourier coefficient, relative to that subgroup. I'm not going to make this precise. So here then is a very explicit manifestation of the structure randomness dichotomy in a group such as F2 to the n, which is what we're sticking with for the moment. This is due to Ben Green from 2005. It says that given an epsilon greater than 0, there exists a constant m that depends only on epsilon, such that whenever A is a subset of F2 to the n, then we can find a subgroup of F2 to the n of codimension bounded by this constant m of epsilon, such that on all but at most an epsilon proportion of the cosets of H, A is epsilon uniform. So, this means that I can split my space or partition my space F2 to the n into a bounded number of cosets of this subgroup, such that on almost all of them, A is evenly distributed. So I say on almost all of them, maybe here and here and here, it's bad, but everywhere else, A looks like a random set. Like graph regularity, this arithmetic regularity lemma has many applications and indeed a number of shortcomings. So for example, it turns out that the dependence of m of epsilon on epsilon is very poor. So Green showed that in general, this function has to grow like a tower in 1 over epsilon. Moreover, turns out it's impossible to get rid of this these cosets that are potentially non-uniform. So there's an example of Green and Sanders that shows that in general, we cannot rule out the existence of a non-uniform coset. This example was never formally published. It is on the archive, but it does play a very important role in what follows. So I would like to have a look at it in more detail. So now I'm choosing F3 to the n to be my group, because it doesn't quite work in characteristic 2. So the Green-Sanders example is the following subset of F3 to the n, namely it's the set of vectors that start with a string of zeros and whose first non-zero coordinate is equal to 1. So what is so bad about this set that it ruins kind of perfect arithmetic regularity for us? Well, it turns out from a model theoretic standpoint, you have an explanation. Turns out the set is not stable in the sense that it contains a very large order property, namely one of length n minus 2. So let me remind you what that means. It means that there are elements a1 up to an minus 2 and b1 up to bn minus 2 in your group, such that ai plus bj is an A if and only if I is less than or equal to j. And this is very easy to see in the sense that you just write down, ai is the element that has a 1 in the I plus first coordinate and zeros everywhere else. So it's the I plus first basis vector. And you as bj, you can take a vector that starts with j plus 1 zeros and then all 2s. So I write this as 2 times e sub j plus 2 plus 2 times e sub n. And you can check that when you add ai and bj, that ends up lying in the set A, if and only if I is less than or equal to j. So Green and Sanders showed in their paper that this set is not linearly atomic. What I mean by that is that it is not possible to decompose F3 to the n into cosets of a bounded index subgroup such that the density of this set is close to 0 or close to 1 on every coset. They actually show something much stronger, namely that the set is not uniform in the sense we discussed before on every positive dimensional subspace. But this is the property of this example that I want to draw your attention to. So you cannot describe it by a decomposition of F3 to the n into cosets of a bounded index subgroup. And it turns out it is really the stability, or the instability of this example rather, that that prevents you from achieving this. So it turns out that if you restrict your attention to stable sets, then you you do actually end up with a linearly atomic decomposition. So this is a result that Caroline and I proved a few years ago, which I will state for you. I know many of you have seen it probably several times. Just for clarity, it says that for all epsilon greater than 0 and k at least 2, there is some n naught such that the following holds in all dimensions greater than n naught. So if you take an A as a k-stable set, then there is a subspace H of some codimension that is bounded only in terms of epsilon and k, such that for any g in fp to the n, either A minus g intersect H is a very small proportion of H, or H with A minus g removed is a very small proportion of H. So what is this saying? So first of all, notice that the number of parts in our decomposition, or rather the index of the subgroup that we find here is exponential in epsilon inverse. Notice also that there are no non-uniform cosets at all, because our conclusion holds for any g in fp to the n. And finally, the conclusion is much stronger than what you get in a standard arithmetic regularity lemma. Not only are you uniform on every coset, but in fact, the density of A on every coset is either close to 0 or close to 1. And the last 2 points are exactly what I mean by linearly atomic. It means that every coset of this decomposition is such that A has density close to 0 or close to 1 on it. We also proved this result in finite abelian groups, and using model theoretic techniques, Conan, Pillay, and Terry generalized this result qualitatively to arbitrary finite groups. And finally, Conan gave a strongly quantitative argument, which is morally the correct, argument in the finite setting. I might also mention that the characterization of linearly atomic sets is open. This is different from the setting of graphs. We might come back to that at a later point in the talk. One other thing to mention is that there are also results about sets with bounded BC dimension. So sets that are stable do have bounded BC dimension, but the conclusions for bounded BC dimensions are somewhat weaker. So you can prove, and this was done by Alan Fox Zhao, Olaf Cisask, and again Conan, Pillay, and Terry in various different contexts, that if your set A has bounded BC dimension, then it is almost linearly atomic, meaning that there is a decomposition into cosets of a bounded index subgroup, such that on almost all of these cosets, your set has density 0 or 1. Now, it turns out that uniformity is not sufficient for uniformity in the Fourier sense, as we described it, is not sufficient for counting progressions of length greater than 3. What I mean by that is that the fact that I showed you earlier, that a set that is uniform looks like a random set when it counts to 3-term arithmetic progressions, breaks down when you replace 3 by 4-term arithmetic progressions. So in particular, there exists a set A, which is uniform, but which contains many more than the expected number of 4-term arithmetic progressions. And I say many more than the expected number, many more than the number you would expect to get if A were in fact a random set. Now, fortunately, this example is very easy to write down, even though I need to change my prime again. So I'm now moving on to p equals 5. Here it comes. I take the set of vectors and f5 to the n for vectors x for which x transpose x is equal to 0. Now, because we're not focusing on the Fourier transform in this talk, I will just tell you that you can show very easily, using some standard computations, that this set is uniform in the Fourier sense. I will also just state for you informally that how you can see that it contains too many 4-term arithmetic progressions. So that the reason for that is the following identity. So for all x and d, we have that x transpose x minus 3 times x plus d transpose x plus d plus 3 times x plus 2d transpose x plus 2d minus x plus 3d transpose x plus 3d is equal to 0. Okay, that was a bit of a mouthful. So why does this tell us that this set contains many more 4-term arithmetic progressions than you'd expect in a random set? Because it produces a relationship between membership in the set of the 4th term of the arithmetic progression based on membership of in the set of the first 3 terms of the arithmetic progression. So in particular, if I know that the first 3 terms of my arithmetic progression lie in the set A, then I know that x transpose x is equal to 0. I know that x plus d transpose x plus d is equal to 0. And I know that x plus 2d transpose x plus 2d is equal to 0. And by this identity, this implies that the final point of my arithmetic progression, x plus 3d, automatically lies in the set A. So, so with probability 1, conditioned on the fact that the first 3 terms lie in A. And this tells us that basically A does not behave like a random set when it comes to counting 4-term arithmetic progressions. In fact, this identity is really incredibly important. It lies at the heart of when we can meaningfully use Fourier analysis to analyze arithmetic structure in our sets. So this is a result of Tim Gowers and myself from around 2006. We showed that you can use this notion of Fourier uniformity successfully if and only if you do not have a quadratic identity of this type. So now that we've ruled out using our the Fourier transform as a suitable notion of randomness for counting longer progressions, we'd better come up with a notion that does not rely on the Fourier transform. And the way to go is to think about similar notions of pseudo-randomness, quasi-randomness in graphs, where the quasi-randomness is sometimes described in terms of the number of 4 cycles in a graph, and an arithmetic analog of that is the following definition, which is due to Gowers. So for a function f from fp to the n into the complex numbers, we can define what's known as the U2 norm as the following average. So actually, we're defining the 4th power of the U2 norm here. So it's the expectation in x, a, b, in fp to the n of f of x plus a, f of x plus b, f of x plus a plus b. And the way you might want to visualize this configuration is as a parallelogram. So this is x plus a, x plus b, and x plus a plus b. And I'm taking an average over a product of the 4 vertices of this parallelogram weighted by the function f. I will give you a more compact way of writing this. Namely, we can write it as the average in XAB again of this capital delta subscript A and B of f of x, where this delta is a sort of discrete differencing operator. So it takes f of x and multiplies it with the complex conjugate of f of x plus h. So you can check that this expression is indeed the same as this. Now, I said that this average defines a norm, or rather the fourth power of a norm, but it's not at all obvious from this definition. But it is actually easy to see that the fourth power of the U2 norm is equal to the L4 norm of the Fourier transform of the function. So again, this wouldn't take very long for me to write out, but we don't have time to see that. Now, this
sorry, can I ask a question? Delta H has only one parameter, but delta AB has two parameters.
Ah, yes. So it means I'm applying delta twice, once with A and once with B. Thank you, Itai. So strictly speaking, it should be delta A, delta B. So this is a shorthand for applying it twice. Okay. Okay. So this doesn't just tell us that that U2 is in fact a norm. It also tells us that it is in some sense equivalent to any norm that involves the Fourier transform. Again, I could make this more precise, but I won't right now. So this means that in some sense, U2 is equivalent to this notion of a Fourier uniformity that we saw earlier. But it does have one important advantage, namely that it's easier to generalize because it's completely combinatorial, right? I just drew you a little picture, and there's an obvious way in which you might generalize this, namely by adding a third dimension to your parallelogram. So I have x plus a, x plus b, and I add x plus c, and I get 8 corners of a cube. We're going to see this picture a number of times, so it's going to disappear very shortly. If I wanted to write this down using a formula, I would do that as follows. So the 8th power of the U3 norm is the average in x, a, b, c. And again here, the delta is delta A, delta B, delta C of f of x. And it's not hard to see that, in fact, you could have written this sort of inductively as the average over the 4th power of the U2 norm of the discrete derivative of f at h. What I claim is that this U3 norm is more sensitive than the U2 norm. In particular, the U2 norm is bounded above by the U3 norm. And in fact, you can imagine generalizing these norms further to UK or uniformity norms of degree k. And there's a whole sequence here that is nested, and they're all bounded above by the L infinity norm of f. So for the purposes of this, the remainder of this talk, I will say that a set.
Can I ask? Sorry, are these norms can also be defined in the non-abelian case, or it doesn't make sense because of the way you have to the iteration depends on Rho, right? I guess.
Yes, you have to be careful. Maybe I'll say a bit about that at the very end.
Okay, thanks.
Okay, so now that we've defined this norm, and I really want to focus on U3 here, can also say what it means to be for the set to be uniform in a way that is useful to us when it comes to counting 4-term arithmetic progressions. So I will say that a set A is quadratically uniform. Really, what I would like to say is if its indicator functions are small in the U3 norm, but that's not quite true. So I need to shift it by the density. But yes, so the set is quadratically uniform if its balanced function, which is the characteristic function minus the density, is small in U3. And now we do have an analog of the earlier fact that I quoted for 3-term arithmetic progressions, namely that if f is quadratic, or if A is quadratically uniform, then it does contain the expected number of 4-term arithmetic progressions. That is the number of 4-term arithmetic progressions you'd expect in a random set. And this is exactly what we would like to be able to say as far as A looking like a random set is concerned. So I quoted this fact. It is a proposition that uses the Cauchy-Schwarz inequality. It's not a deep fact. The depth of this fact kind of lies in the definition rather than the proof of the fact itself. But yeah, let me not say more about this. So we now have an appropriate notion of quasi-randomness, pseudo-randomness, and we can count. Now, the question we asked earlier very briefly was, okay, so if your set is uniform, then I can count. What if it is not? So what this means in our setting here is that what if you have a function whose U3 norm is large? And the first thing you might want to do is actually find out when the U3 norm is really, really massively big. And I've given you an example here. So I take e to the 2 pi I x transpose x over p. That will have U3 norm equal to 1. And that's because of the following quadratic identity. I will try and write this down with some ... So for all x, a, and b, and c, I have that x transpose x minus x plus a transpose x plus a minus x plus b transpose x plus b minus x plus c transpose x plus c plus x plus a plus b transpose x plus a plus b. You get the idea. And the final term of minus x plus a plus b plus c transpose x plus a plus b plus c. All of that is equal to 0 for all x, a, and b, and c. You can work that out. What is this? This is a signed sum over the squares of the vertices of our 3-dimensional cube. You can also think back to the sort of Fourier case. What can we say if the U2 norm of the function is large? Then we said we get a large Fourier coefficient, and that sort of tells you that your function correlates with a function of the form e to the 2 pi I x transpose times some r. So it's therefore not unreasonable to conjecture that if your set is not quadratically uniform, then it might look a bit like the level set of a quadratic. And a formal statement to this effect is the following. This is due to Green and Tao, based on lots of ideas of Gauss's in his proof of Semradi's theorem. This is in fp to the n. So if you have a function f, a bounded function f, such that its U3 norm is at least delta, then there exists a quadratic phase function phi with which f correlates to the tune of c of delta. What is a quadratic phase function? It is a function of the form e to the 2 pi I q of x over p for some quadratic form q on fp to the n. So I won't say much about the proof, the idea is that you do it by induction, but it requires an ingenious combination of various results in additive combinatorics, including Freiman-Ruger, Bogel-Yuboff, all sorts of things, and some Fourier analysis, and it's probably the highlight of an entire graduate course. But using this, you can prove Semradi's theorem, or at least an analog of Semradi's theorem in FP to the n. I should pause for just a second here and say that this statement is definitely very, very specific to FP to the n. The quadratic objects that you encounter in more general finite abelian groups are much more complicated than the ones that I have shown to you here. But that's actually the reason why we work in this setting, at least for now. You also have to be a bit careful in small characteristic, in particular when you go to higher order uniformity norms. And actually, I should have said that this theorem for p equals 2 is due to Samorodnitsky. Okay, so this is a really, really deep and kind of fundamental result in arithmetic combinatorics. And what it allows you to do is it allows you to decompose fp to the n into the level sets of what we call a quadratic factor in such a way that your set A looks kind of quadratically uniform with respect to every part of that factor, or almost every part of that factor. Now, what is a quadratic factor? It will be given by a collection Q of n by n symmetric matrices, m1 up to mq over fp, and a collection L of vectors in fp to the n, which I'll call f1, r1 up to rl. And so what I claim is that we can decompose our space in such a way that any set A is quadratically uniform with respect to almost all of the level sets of a quadratic factor. Now, what do these level sets look like? We also call them atoms. They are sets of the form x in fp to the n, so they're such that x transpose m1 x is equal to sum a1 in fp, x transpose m2 x is equal to sum a2 in fp, and so on. And I also have a bunch of linear constraints using the vectors r1 up to rl. So such a set is a quadratic atom. That means, so what have I said? I've said I can split my space into, so essentially there's an underlying linear partition from these linear constraints. And then on top of that, I have some quadratic pieces, which will hopefully kind of split each of the linear ones in some way. And for such a partition to be useful, or I really need it to consist of not too many pieces. So that's a notion expressed by the complexity of this quadratic factor, which is roughly speaking the number of linear pieces and the number of quadratic phases that you use. You also need to make sure that the individual matrices that you use to construct this factor, and in fact any non-trivial linear combination of them, has a sufficiently high rank. This is really important in order to make sure that the individual pieces of your factor have roughly the same size. So we have a notion of rank associated with the factor, which is the least rank of any non-trivial linear combination of the matrices. This rank makes a lot of statements a little bit complicated. We'll get to that in a moment, and that's part of the reason why I'm being rather informal today. So decomposition theorems of this type have been developed by many people, amongst others Green and Tao. Tim Gowers and I had a different approach a few years ago. There's also some significant literature on this in theoretical computer science. So what I will give you on the next slide is sort of the simplest possible quadratic decomposition theorem that I'm able to state, and it is in this form due to Green and Tao. So this is what we call a quadratic arithmetic regularity lemma. There's some quantifiers at the beginning, which I will gloss over for now. And yes, it's stated for a function rather than a set. It says that given any function from fp to the n into -1, 1, there's a quadratic factor of some complexity with the following properties. So we said it'd be desirable for this factor to have bounded complexity. That means to consist of a bounded number of parts. That is, you can indeed ensure that. We also said it would be desirable for the rank of this factor to be high. That actually turns out it needs to be high relative to the complexity. So you need to be able to choose any function omega-1 of the complexity of the factor to be able to work with the factor afterwards. And where is the decomposition? Well, here it is. I can write the function f as a sum of three functions f1, f2, f3, where the first part, f1, is a very structured object, namely it's the average of f, with the function that is given by the average of the function f over the atom of the factor that x lies in. So what this projection here does is you take your factor and, at the point x, this function f1 will simply be the average of f on the atom that x lies in. So in particular, the function f1 will be constant on each atom. So this is a very structured function because there's a bounded number of pieces in your decomposition. F2, on the other hand, is the random looking part of the decomposition. So that's a function that has small u3 norm. When I say small u3 norm, it's in fact tiny u3 norm. I can make it as small as I like with respect to the complexity of this factor. And finally, there's a term f3, which we would really like to get rid of most of the time, but can't in general. That's a term that is small in the L2 norm. And that is responsible for us having some quadratic atoms in this decomposition on which we do not have uniformity necessarily. So these are sort of the non-uniform quadratic atoms are hidden in this error term.
Julia?
Yes?
Could I ask a small question here? So in the linear atomicity theorem, as you stated at the beginning, it seemed like you could get the density on the atoms to be close to 0 or close to 1. Is that kind of thing possible here, or are we really tied?
Yeah, but that's exactly where we're headed. So,
sorry.
This is a very general. So, Jordan, yes, this is a great question, and I was literally about to ask that question, right? Because we're at a point where we can actually start asking some questions about. This is a decomposition I can make for any function, or any set, if you like, right? But are there conditions that ensure that we can place on the set that we do indeed end up with these ultra nice decompositions where you have density 0 or density 1 in every atom, rather than just having uniformity? That is exactly the question that this entire project addresses. Yeah, what local or combinatorial notion will characterize this really strong quadratic structure in the sense that you actually do not have an error term and that you have these strong density conditions on every single atom, right? So in order to answer, or actually not quite answer this question, but we have to take one step back and think about what characterizes quadratic structure in the first place. So, and we'll take one further step back and think about what characterizes a subgroup, right? A subgroup is characterized by the fact that if I take two elements in it and I add them in the case of abelian groups, then I'm still in my subgroup, right? It actually turns out that cosets of subgroups are also characterized by the absence of the two-order property. So a coset of a subgroup has no two-order property because for all x1, x2, y1, y2, I can write x2 plus y2 as the following sum, namely x2 plus y1 plus x1 plus y2 minus x1 plus y1. So if I know that x1 plus y1 and x1 plus y2 and x2 plus y1 are in my subgroup or in the coset of a subgroup, then x2 plus y2 are is automatically in there also, and therefore, no coset of a subgroup can have a two-order property. And this is a characterization, right? So let's ask the same question: what characterizes a quadratic atom? So it's not stability, or the absence of an order property. So in fact, quadratic atoms are unstable. We proved that in our paper. It's not very hard to see. And in fact, it's worse than that. They even have unbounded VC dimension. But they do have another very nice property, which I'm about to draw a picture for. They do have the following property. So I'm going to draw my cube again. You'll see lots of pictures of cubes today. So I'm going to label the vertices a little differently. I'm going to give each vertex 3 coordinates, namely x, y, and z. So I'm going to put x1 here, x2 there, y1 there, y2 there, z1, 2, z2 there. So this point up here, for example, is labeled by x2, y2, z2. And okay, what is the property that the quadratic atom has? It has the property that if I know that 7 of my 8 vertices of the cube are in the quadratic atom, then I know that the 8th vertex has to be in the quadratic atom also. Let me just copy this for future use. Why is that? That's because of the identity that, in some form I've already shown you I've just used squared here as a shorthand for the vector transpose times itself. Because of this identity, it's true that for all x1, x2, y1, y2, z1, z2, the 8th vertex of the cube, which was the one at the front right here, x2 plus y1 plus z1, can be expressed as a linear combination of the other 7. And therefore, if each of these lies in my quadratic atom, then the 8th one will be forced to do so also. And now this is a basis for a definition we made, which attempts to generalize the order property for the purpose of identifying a combinatorial property that produces strong quadratic regularity decomposition. So given a set A in Fp to the n, we say that A has the LHOP2 if there exists vertices x1 up to xl, y1 up to yl, z1 up to zl, such that xi plus yj plus zk is in A, if and only if k is strictly less than I plus j. So let me make a few remarks about various bits of this definition. So we chose the letter H to stand for hyperplane, and that is simply because a more general, if you think about, if you wanted to draw a picture of this, these 3 sequences xi, yj, and zk give rise to a 3-dimensional cube for which the portion cut off by a hyperplane is not in the set, but everything else is. The subscript 2 here stands for it denotes its three-dimensional nature. So this is a recurring problem in arithmetic combinatorics, that there's a sort of mismatch between dimension and and the degree of the polynomial involved in the structure. You can, this is a truly ternary notion, so I want to stress that. This looks a little asymmetric, right? Because it singles out one of the variables, but you can actually, you know, just reparameterize them, reorder the xi's, and make this completely symmetric. And of course, there's a non-abelian version, there's an infinitary version, etc., etc.
Julia, Julia, I would just like to kindly remind you about the time.
Yes. Do I have another? I thought I had until 5.
Oh, okay. Sorry. Okay.
Okay.
Yeah.
Sorry about that.
2 more minutes. Okay.
Yeah. Okay. So, a quadratic atom turns out does not have the 2 HOP2. And again, it is because of this identity, because it tells you that if you've got 7 vertices in your atom, then your 8th one will be in there also. And that rules out having a picture where all 7 guys are in your set and the 8th one is not. So you can construct other sets that do not have the LHOP2 for some L by, you know, taking unions of atoms, but it turns out also unions of some cosets if you do it carefully. So then there's a question, a natural question. Is it true that all sets that avoid the LHOP2 for some L are quadratically atomic, in the sense that I can decompose FP to the n using a high rank quadratic factor of bounded complexity in such a way that on all atoms, the density of A is close to 0 or close to 1? That is the question that Jordan was asking earlier. Okay. And it turns out that the answer is very unfortunately no. So I really wanted this to be true because I thought it would be very beautiful. But the answer is no. And the reason the answer is no goes back to the Green-Sanders example that I showed you earlier. So that has no 4 HOP2, but we proved that it is quadratically, it's not quadratically atomic. So you cannot decompose it nicely into these 0, 1 quadratic atoms. The fact, you know, this held us up for a really long time. Yeah. Now, it turns out you can still prove some strong quadratic structure properties for sets that do not have the HOP2. But in fact, these decomposition properties are true for a slightly larger class of sets. So we also made the following definition, which generalizes the definition I just showed you. This is the FOP2, so for functional order property. It says again that, you know, your set has LFOP2 if there exists x1 up to xl, z1 up to zl, such that for any function f from L squared to L, you can find y1 up to yl such that whether or not xi plus yj plus zk is in A depends exclusively on whether k is less than or equal to f of ij. So stable sets that do not have the order property, of course, I mean, trivially do not have the hyperplane order property. And again, trivially, they do not have the functional order property. So in particular, our quadratic atoms are free of these FOP2 objects. And we can prove that their unions are also. We can also prove that NFOP2 implies NIP2, where NIP2, well, IP2 is a higher dimensional version of VC dimension. defined in terms of shattering a box. So I will come to the final couple of slides. What we actually prove about NIP2 and NFOP2 is the following. First, NIP2, which is a weaker result. We proved that these NIP2 sets are almost quadratically atomic in the following sense. If your set A has no IP2, then I can decompose FP to the n using a high rank quadratic factor of bounded complexity in such a way that on almost all of the quadratic atoms in this factor, the density of A is close to 0 or close to 1. This is on almost all, not on all of them. But in fact, we can say more for sets that are actually that actually lack FOP2 instead of just IP2. Now, what could more mean? Because we already said not having FOP2 cannot imply that you are, perfectly quadratically atomic. What we prove is the following. We proved that NFOP2 sets are almost quadratically atomic with linear error, namely in the following sense. So I can decompose FP to the n using a high rank quadratic factor of bounded complexity in such a way that on almost all of the atoms, the density of A is close to 0 or close to 1, which is what we had before for NIP2 sets. But in addition, the set of atoms where we're not close to 0 or close to 1 with the density will be contained in a small number of purely linear atoms from the same factor, I should stress. So let me draw a quick picture and then I'll stop. So here is my the linear part of the factor with an overlying quadratic part. What the NIP2 result says is that we have a small number of error atoms where we don't get this nice 0, 1 density. But what the NFOP2 result says is that actually all of the error atoms are contained in the same or in a small number of linear parts here. Okay, so there's additional structure to the error. If you want to look up this particular theorem in our paper, it's 1.33, where you'll find a more formal statement. So I'll stop here and take some questions. Thank you very much.
Thank you. Are there any questions from the people here or from the audience online?
Julia, can I ask one more?
Of course.
So this Green-Sanders example, which you show is not linearly atomic or quadratically atomic. Do we know, are there lower bounds for if I want to have some algebraic map from the some polynomial map from the elementary abelian P group to some other elementary abelian P group, so that on the fibers the density is always close to 0 or close to 1? Do we have any kind of bounds on like what degree of an algebraic map you would need or anything like that?
So if I understand your question correctly, so I would conjecture that actually the Green-Sanders example basically will destroy your hope of all the way up, right, for any degree.
As it has yours in this initial case. Really, so it's somehow irreducibly.
It's irreducibly bad. Yeah.
Okay.
Is I think what the conclusion we've come to. So we do have some, and this is to do with actually our confidence in that regard stems from our analogous work in the hypergraph setting, which I've not talked about at all today. But you can basically use the Green-Sanders example to just construct hypergraphs of arbitrary arity. So you can construct them for, S uniform hypergraphs at any S, and these will have not optimal decomposition properties, essentially, for whatever notion of hypergraph irregularity you want to define.
Julia, we also have a question in the chat. Maybe you can open it.
Just a moment.
I can't see.
Do we have examples of types of sets that obey these higher order stability properties?
I mean, I guess you could take like something analogous in like FP to the omega and like some bilinear form. But for example, you can get, because being NFOP implies that you have bounded VC2 dimension, you can find these in like the random ternary hypergraph, which is simple. So is that kind of oh, he doesn't mean simple theories. Okay, sorry.
So may I ask, in particular, do we know that algebraic sets satisfy this L and FOP too? Do we know algebraic sets satisfy this higher order stability condition?
Do we know that there are sets that satisfy it?
Algebraic sets, variety. Do varieties satisfy this higher stability condition?
So anything that anything of the form that I wrote down that might constitute a quadratic atom will satisfy this condition.
Right.
And I should probably I can show you one more slide that says that, you know, this is really a it is a non-trivial result, because we also have a quadratic version of the Green-Sanders example, which looks a lot like the linear version. So I constructed, you know, from a bunch of matrices that are essentially, you know, orthogonal, in the same way that you construct the linear example. So you take kind of unions of smaller and smaller instances of these quadratic atoms that are disjoint. So these guys are almost quadratically atomic, but they are not almost quadratically atomic with linear error. So you cannot force the error atoms to kind of be nicely contained in this linear structure. And so in particular, you know, this is an example that does have FOP2 for arbitrarily large, you know, LFOP2 for arbitrarily large L.
Any more questions? Okay, so let's thank Julia again. I think we'll resume at 1:35, right? It says 1, okay, whatever you decide. Whatever it says on the schedule. Yeah, I think it says 1:35. Okay. Yeah, 1:35, okay.